So with inverse trigonometric functions 5.3, the important thing is to understand what an inverse means. And this is a quick review of Algebra 2. You've got a function, rule f, and it takes an element in the domain, or the input. You can kind of think of what your input is. And then it maps it, according to whatever the function rule is, over here to this y value, which is your output, or your range. So what an inverse does is it takes all of the y's, basically your output, and it maps it back to the domain, the old domain, and that's called the inverse of a function, f inverse. So all of the x and y pairs are switched. The vertical line test, where you can draw a vertical line across a graph, and if it only intersects one time, then it's a function. If it intersects more than once, it's not a function. So it's intersecting here and here. So the deal is with these functions and their inverses is now we're going to take this function and we're going to reflect it about this line y equals x. We'll get into more details. So now a function has to pass what's known as the horizontal line, or the horizontal rule, and a function must be one-to-one if it's going to have an inverse that's defined. And I'll show you why that makes sense in 1 second. So this function right here, as you may recognize, I hope you recognize it, it's sine of x. Okay, so with sine of x, you can see that it's not one-to-one over all of the real numbers, right? So we have to restrict it if we're going to talk about the inverse, because when I reflect this function, it wouldn't be, if I reflected it as is, you'd have a graph that looks like something like this, and it would be like that. So you can see clearly it's not going to pass the vertical line test, right? So if we restrict this function to a certain domain right here, and they're saying, okay, well, from negative pi over 2 to pi over 2, sine x is the dashed line here. And so we're just going from negative pi over 2, which is right here, to pi over 2. And if I restrict that graph, then I can define an inverse for sine as long as it's between negative pi over 2 and pi over 2. And I can draw it by symmetry about this line y equals x. Everything is reflected about the line y equals x, and the way I think about that is because with inverses, all the x's and y's are switched. So everything gets reflected about that line. So you can see sine inverse here of x is going to look like this. And in this case, it's going from negative 1 to 1 for the x values, which were the old y values, and it's going from negative pi over 2 up to pi over 2. So when you're evaluating things with inverses in them, where is negative pi over 2 to pi over 2 on the unit circle? Because that's really going to help you. So remember, negative pi over 2 would be down here. Okay, so sine inverse will be defined all the way from negative pi over 2 for angles between negative pi over 2 and positive pi over 2. So if you get an angle that's outside of that, you have to think about what is the equivalent angle between negative pi over 2 and pi over 2. And that's going to be the trickiest part when evaluating expressions with inverse trig functions in them. So this is one property. Inverses undo each other. So you can say if I apply the inverse, sine inverse of a sine function, I get out y as long as y is between negative pi over 2 and pi over 2. So that's the rule. And similarly, sine of sine inverse of x is equal to x, this stuff, as long as x is between negative 1 and 1. This will all make sense in a little bit. I just did a print screen of sine and arcsine. You can actually type in arcsine, or you can find it on your function button in Desmos if you wanted to look at that. And then in your graphing calculator, it's sine inverse. You have to use the second button. So notice in this that sine, arcsine, is only defined for that little portion here. All right? And sine x, it's defined over all of the real numbers. So we've talked about this in chapter 1. When we are finding angles, you have to use sine inverse if that's the thing that you don't know. So once again, with inverses, it's I'm asking the question, the sine of what angle equals -1? So the sine of what? Well, -1 sine is down here at 3 pi over 2. But 3 pi over 2 is not in our range. Remember, going back to the graph, we're going from -pi over 2 up to pi over 2. So that's what sine is defined on. So you have to give an angle from -pi over 2, which keep in mind it is equal to 3 pi over 2. But on the graph, if you're thinking about it, it's a different value, up to pi over 2. Okay, so then you say, all right, well, the answer would be that it's equal to -pi over 2. If you type this into your calculator, and you should be in radian mode, you say sine inverse of -1, you're going to get a value, negative 1.57, which is actually half of pi. So if you do pi divided by 2 just to verify that, you got that. So I want you to be able to find the exact values, not just the estimated values. So you can use a calculator on an exam or on your homework, but if you don't give me the exact value, it won't cut it. Okay, the next example, you can work inside out. Now remember I said sine inverse and sine, they undo each other, but you have to remember that this angle pi over 3, this needs to be between -pi over 2 and pi over 2. But it's okay because sine of pi over 3, I can just evaluate what sine of pi over 3 is. So sine of pi over 3 here, remember it's the y value, so that's equal to the square root of 3 over 2. So my new problem becomes sine inverse of the square root of 3 over 2. Well, what does that mean? Sine inverse of square root of 3 over 2. I'm asking what angle between -pi over 2 and pi over 2 gives me an output of root 3 over 2. And in that case, it is, in fact, pi over 3. Gives sine to be, to be root 3 over 2. And that has to be between -pi over 2 and pi over 2. So we're going to look at number 12, which is sine inverse of sine of -5 pi over 6. So if I start inside, it's sine, finding out what sine of -5 pi over 6. There's no restrictions there with sine because it's just the sine function. So where's -5 pi over 6? Well, here's 1 pi over 6. Here's 2 pi over 6, here's 3 pi over 6, here's 4 pi over 6, here's 5 pi over 6. Okay, going backwards because it's negative. And then you look at the y value, that's -1/2. So we can say that that's -1/2. So if I substitute this in for all of that right here, now I'm looking at the subproblem is sine inverse of -1/2. So now I'm looking the sine of what angle between -pi over 2 and pi over 2, remember sine inverse is defined that way, gives -1/2. So here we go, we're in between -pi over 2 and pi over 2. Where is sine equal to -1/2? Well, this is your only option right here. What is that angle? That's 11 pi over 6, but it's not between -pi over 2. Oh, no, no, no. So instead we have to say it's how many units are you from here? You're going in the negative direction. That would be -pi over 6. So if you check that on the calculator and you evaluate this, you can see, so we're going to say sine inverse of sine, and that is -5 pi divided by 6, close parentheses, and you're going to get that value, which let's see if that is pi over 6, and it's a negative, so you can see that those are the same values, I just didn't add a negative, but you get the idea. So if you would put, for instance, 11 pi over 6 instead, remember that's not in basically the domain of the inverse function, or I should say the range of the inverse function, because everything is switched. Okay, so moving on to cosine now and looking at cosine inverse. This is the cosine graph right here. So cosine goes on and on. So it's not a one-to-one function, cosine of x. So we have to restrict it. And in this case, since cosine it goes from here to here, would be a nice spot to restrict it, okay, because then if I start going up again, it wouldn't pass the horizontal line test, and so when I reflected about that line y equals x, it wouldn't be a function. So if I go from 0 to pi in this case, that will allow me to come up with a function that will also pass the vertical line test. So that's what they're doing right here. We're going from 0 for the original function to pi. That means now I'm going from 0 on here up to pi, and now these are my y values. And my x values, well, the maximum that cosine gets is up to 1, and the minimum it can get is -1. So your inputs for your inverse are from -1 to 1, and you can see the graph. So same goes, they undo each other as long as your y values are between 0 and pi. And similarly, they undo each other as long as your x values are between -1 and 1. And that's for the inverse function. So now the trick is on the unit circle, we're going from 0 to pi. Okay, so everything up here we can work with in the first and the second quadrant. So when we're dealing with that for cosine inverse of 1, well, it's clear that cosine inverse of 1, and that's the x value, so the cosine of what angle gives a 1 between 0 and pi? This is your only option right here, when you have 0 radians. So we can just say that that's equal to 0. Okay, that's pretty straightforward. Now we've got to work on this value. So we've got the cosine, and we're going to work inside out, of -pi/10, and we can just evaluate that like we've always been doing. So we go to -pi/10. Well, where is -pi/10? That's going to leave me, in this case, I'm going to be over here on the negative side. Actually, the angle -pi/10 is going to be somewhere here. That's a smaller angle. Now, you don't even need to know what it is. It's something. We'll just say it's -pi. This is where it gets a little crazy, over 10. Because I'm going down and I break up pi from here all the way here, 10 equal parts. So that's somewhere in the fourth quadrant. Okay? But cosine doesn't live there, right? Cosine inverse, it's not defined from there. So cosine inverse is defined between 0 and pi. And so what would reflect? Well, these x values, do you agree, are going to be the same whatever they are. So this value right here, this x value, is going to be the same as this x value. They're both going to be positive, right? So I can say that that's equivalent to positive pi/10 by symmetry. All right? So then I know that this undoes this, and it has to be in between there. So we're going to say whatever that value is, and we could even say call it star. So if we do that, this might get a little crazy, but cosine inverse of star. Well, cosine of what angle gives you star? Well, here's star down here, but star is also up here because it's the x value, and in the first and fourth quadrant, cosine, the x values are positive and the same by symmetry. So we can say then between 0 and pi, it's got to be that positive pi/10. And if we verify that with a calculator and we type in cosine inverse of cosine of negative, whoops, we just need a negative sign, pi divided by 10, close parentheses, we get that value. And then just to check that, see, that's a positive output. So it's not going to give us that -10. To check that, that's second pi divided by 10. That is that value that we want. So with tangent, when we're defining tangent, this is the graph in the red of tangent, and it's got these multiple asymptotes here, but it just keeps going on, and once again, it's not one-to-one. So if we restrict it and limit it to between negative pi over 2 and pi over 2, that's going to be our inverse function. So now if you look at this graph, tan x is this dotted line here, but tan inverse here, it's restricted between pi over 2 and negative pi over 2 now on the y-axis because everything's switched. And look at this. If you think about the y values of tan inverse, they just, or of the original function f, they go on forever and ever because that's an asymptote. So the y values of the original function of f, they just continue on and on and on. So now when we're thinking about what the inputs for our inverse function, they can go on forever and ever and ever. They can be any value. So it's all real numbers in this case when we're thinking about the scale of tangent and the inputs for inverse. So for number 2, it's asking you to find tan inverse of negative 1. And now since tangent we said was defined between negative pi over 2 and pi over 2, again, kind of like sine. So here's negative pi over 2 and here's positive pi over 2. So we have to look for values. The tangent of what angle will give me a negative 1. Remember that the ratio of tangent is y over x. So this is where we get a negative 1, and this is where we're going to get a positive 1. So in this case, it has to be this angle right here, from here to here. But this angle, 7 pi over 4, is not between negative pi over 2 and pi over 2. What angle would be? It would be negative pi over 4, because that is between negative pi over 2 and pi over 2. And if you check that on your calculator, you've got tan inverse of negative 1. And remember, we're finding exact values, so this is just a way to check it, okay? It's not going to give you the correct answer on an exam because I want you to find the exact values. And once again, it is negative if I just check that, but the approximation of it is correct. Okay, so if we look at 4 pi over 3, the tangent of 4 pi over 3, I'm starting with the inside function for number 16. I'm going to go, here's 1 pi over 3, here's 2 pi over 3, 3 pi over 3 is pi, 4 pi over 3. Okay, tangent is the ratio of y over x, and since there's two negatives, it's going to be a positive. So it's root 3, over 2 over negative 1 over 2. Two negatives make a positive. Like I said, the 2's cancel out, and so you're just left with the square root of 3. Okay, so now I'm looking for what tangent inverse is equal to the square root of 3. So the tangent of what angle will give me the square root of 3? Well, remember, we are between negative pi over 2 and pi over 2, so somewhere in here I need to get a positive ratio. Well, I'm not going to get a positive ratio right here because that would give me a negative value because it'd be negative root 3 over 2 over 1/2. So it has to be up here at pi over 3. This would give me, so if we just evaluated just tangent of pi over 3, do you see that that would give me square root 3 over 2 over 1/2, which would also be the square root of 3. Okay, so the angle that makes this true is positive pi over 3. And if we check this on our little calculators and we say, okay, tan inverse of tangent of 4 pi over 3. So 4 pi divided by 3, close parentheses, and we have 1.04. And if you just check pi divided by 3, you get 1.04. Okay, so looking at the function cotangent of x, you can see remember it's shifted over, its tangent shifted over, and flipped. And so it's defined the vertical asymptotes because it's sine over cosine, and cosine is 0 when, um, excuse me, it's cosine over sine. Sine is 0 at 0 and pi and 2 pi and 3 pi. So if we define a one-to-one function, we would need to limit it to 0 to um, pi, basically. Now, I keep forgetting to mention that another way to write cotangent inverse, and you'll see this in a lot in calculus, is arc cotangent. And if you type it in like that, that will give you the inverse. So they say that in the book. So just be prepared for seeing arc cotangent as well as cotangent to the -1. And since we're on that subject, note that the cotangent, like this -1 of a value x, this is definitely not equal to 1 over cotangent of x. That's a common misconception that students think that this -1 just means you bring it down below. It's a totally different meaning, okay? The -1 is not an exponent. It's just a symbol to denote inverse. So here we have it defined. We're going from 0 to pi, and then it's all real numbers just like tangent. And here's the graph of cotangent inverse or arc cotangent. So secant and cosecant, you can look at the graphs, the original graphs, but this is the range. Basically, we're going from -pi/2 to pi/2, and as long as your x values are greater than or equal to 1, and remember that's because you've got values, your graphs are above. Remember how they kind of curve like that? So they don't go in between -1 and 1. They can equal -1 and 1. Actually, I should have drawn my x-axis below or in between there. So you can look at the graphs to verify that. And we're going from 0 to pi with secant. Remember, secant is 1 over cosine of x. So the way to remember this range, secant of x equals 1 over cosine of x, well, remember cosine inverse, it's going from 0 to pi, and so the same with secant. And cosecant is of x, just as a review, is 1 over sine x. And remember with sine x, we went from -pi/2 to pi/2. So that'll help you remember your ranges. And then just to keep in mind that they're greater than the absolute value of 1. That means they can be less than, so that means that x can be less than -1 or, or equal to, or x can be greater than or equal to +1 by definition of absolute value. So I just thought I'd take a moment to show you secant x. So secant x, you can see if we start here at 0 and go to this value, pi and -1, do you see that this function is 1 to 1? Because if I have a horizontal line, it will never intersect twice. As soon as I go beyond, right here, beyond pi, then it's not defined. So that's why it works for secant. Remember, secant is 1 over cosine, and so cosine inverse is from 0 to pi, just like secant x is from 0 to pi. And then let's just graph arc secant so we can see it of x. And so there is the lovely graph of arc secant of x. Okay, so number 18 is cotangent inverse of cotangent of 4 pi over 3. Work inside out. So first just find out what cotangent of 4 pi over 3. This is going to make you guys really good at your just evaluating trig functions. So here's 1 pi over 3, 2 pi over 3, 3 pi over 3, which is pi, 4 pi over 3. So cotangent is x over y, opposite of sine, so it's -1/2 over negative square root 3 over 2. And in this case, the 2's go away. 2 negatives make a positive. It's 1 over the square root of 3. Okay, so the problem is that 4 pi over 3 is definitely not in our range, and for cotangent we're going from 0 to pi, just like cosine. So from 0 to pi, I have to figure out somewhere where it's equivalent that I get this positive number of ratios, okay? And I'm also doing something that's where it's x over y. So do you see that at positive pi over 3, if I looked at the cotangent of pi over 3, that would be the same thing because that's x, which is 1/2 in the first quadrant, over the square root of 3 over 2, which is equivalent to 1 over the square root of 3. So when I substitute this in, if I think about it, I've got cotangent, whoops, not cosine, cotangent inverse of 1 over the square root of 3. I'm asking myself the cotangent of what angle gives me positive 1 over the square root of 3 between 0 and pi? Well, that is pi over 3. Okay, number 20, secant inverse of secant of 6 pi over 5. Secant, or 6 pi over 5, this gets you really good with your fractions. Pi is over here, so if I have 1 pi over 5 somewhere in between here, it's not in this angle, but it's pi over 5, 2 pi over 5, 3 pi over 5, 4 pi over 5 pi over 5. 6 pi over 5 is going to put me somewhere in quadrant 3. Excuse me. So I know that secant is 1 over cosine. Cosine in quadrant 3 is going to be negative, less than 0. So this value is negative. Okay, whatever it is. I don't even need to know what it is. I know that these undo each other, but we can only deal with secant. Secant goes from 0 to pi. So we're up in this region. Well, where do we also have a negative cosine? We have a negative cosine in this quadrant 2, not 3. So in quadrant 2, cosine would also be negative. That would give you a negative secant value. So wherever it is, it's going to be up here. And so how would I get that? If I'm, here's basically 5 pi over 5, because that's equivalent to pi. So one more would be 6 pi over 5, wherever that is, somewhere between there. So then one back would be 4 pi over 5. So this answer would equal 4 pi over 5. Whoops, sorry about that. So something like number 22, it gets a little tricky because you're not given any pi's or reference to the unit circle. So what you need to do is you need to say, okay, well, I'm going to start with the inside. That's what we like to do. We're going to say let sine inverse of 4/5 equal some angle, and we're going to call it theta. So by definition, if I switch these around, then I undo my inverse. So it's the equivalent to sine theta is equal to 4/5. Remember, sine of what angle is equal to 4 over 5? And I dropped my negative, but it is a negative. Now this also tells me that sine theta, what quadrant would give you a negative 4/5? In this case, it's quadrant 4 or 3. So we are in quadrant 3 or 4 here. So if I do that, then I can set up a triangle. Well, actually, I'm going to use Pythagorean theorem on this one. So if we say, remember if Pythagorean theorem was sine squared theta plus cosine squared theta equals 1. And I'm trying to find what cosine theta is because now, since I did that substitution, I'm looking for cosine theta. Okay? So cosine theta is sine squared theta and cosine squared theta. I'm going to substitute what I know. I know that that's negative 4/5 squared plus cosine squared theta equals 1. And there's an example in your book with this, so if you get confused. So if I solve for cosine squared theta, I get 1, which is equivalent to, let's get the common denominator, 25 over 25. It's time to go home when you start writing different numbers. That ends up being minus 16/25. I just brought everything over to the right-hand side. So now I have cosine squared theta equals 9 over 25. And so that tells me that cosine theta is equal to the square root of both sides. So that would be 3/5. So I know that cosine theta is equal to 3/5. And I didn't finish that. I said that this right here, this could live in quadrant 3 or 4, but actually I know it's quadrant 4 because we're dealing with sine inverse, and sine inverse can only live between negative pi over 2 up to pi over 2. So that's where that's important, that range there. So because it's between those two, I have to go into quadrant 4. And in quadrant 4, I know that cosine is positive. So cosine theta is greater than 0 in quadrant 4. So my answer is going to be positive 3/5. So I can say that the cosine of theta is equal to 3/5, or this original thing. So for number 24, what I'm going to do is I'm going to set this first thing, sine inverse of 5/13 equal to alpha, and I'm going to let the second thing equal beta. And so if I do my work, I've got sine of alpha is equal to 5/13, and cosine of beta is equal to 5/13. Well, go way back to right triangle trigonometry. So if we're dealing with sine of alpha and a right triangle, remember what that means? Alpha, or sine, is opposite angle or opposite side over hypotenuse. So what's your reference angle? You got a right triangle. Here's alpha. So the opposite leg would be 5 and the hypotenuse would be 13. Okay? In cosine, cosine deals with the adjacent leg over the hypotenuse. So whatever your angle is, you've got 5 over 13. Well, look at how convenient this is. If I use this angle and if I say, well, what if this is beta? Because it works, cosine of beta is adjacent leg over the hypotenuse. And in this case, I know it works. So what does alpha plus beta, because that's what we're dealing with here, alpha plus beta equal? Well, alpha plus beta is going to equal 90 degrees because this is the 90-degree portion. This 90 plus these two angles adds up to 180. So alpha plus beta is equal to 90, but since we're dealing with radians, we're just going to call it pi over 2. So this answer is just pi over 2. Okay, I'm not going to have you prove too many identities, but I did give you number 27, so I'll do number 26. And first we're going to start with letting sine inverse of x equal theta. So that means that the sine of theta is equal to x. Well, once again, we're going to do some right triangle trigonometry. So here's a right triangle. Here's theta. And x is opposite from this angle theta, here's my right angle, over the hypotenuse. So it's x over 1. Well, how do I find this side right here? Well, this side is going to equal, we'll just call it a for now, a squared plus x squared equals 1. So a is equal to 1 squared, which is just 1. So you have 1 minus x squared, and then if you take the square root of it, you get the square root of 1 minus x squared. So that's what this side equals right here. So this a is equivalent to the square root of 1 minus x squared, if you can visualize that. Now remember, since we let this sine inverse equal theta, that goes in right here. So really I'm looking for the cosine of theta. Well, the cosine of theta is adjacent over hypotenuse. And according to this triangle, the adjacent leg is this square root of 1 minus x squared over the hypotenuse, which is 1. And so that's equal to, I can say then that cosine of theta is equal to the square root of 1 minus x squared, QED. You do this a lot in calculus when you're taking the derivative and integrating. It's important to know this property and how to find the other angles.